Hi, I'm Professor Goins, and welcome to the Math Professor's YouTube channel. If you find our content to be useful or interesting, please consider subscribing. Also, any of those free, quick, and easy things that you can do would be like our videos, share our videos, comment on our videos. Any little bit of interaction would help us out and help us to reach more people, which we'd ultimately like to grow. We're a very small channel at this point. Let's go ahead and start the video. What I want to talk about is the derivative of a power series. Now, a power series is a function that has the following form. It's an infinite series that has the following components. Cn times x minus a to the n. Cn is a sequence of real numbers, and a is a fixed real number. Now, this, of course, is a special type of an infinite series, again, called a power series, where notice basically the idea is if I expand this, it's essentially going to be a polynomial with infinitely many terms. Take a look at a specific example. Consider this function right here. F of x is the sum from 0 to infinity, 1 over 2 to the n, x minus 3 to the n. So again, this does fit the form of a power series where the exponents on x are all positive integers, and you've got these coefficients come from a sequence. If I expand this, well, if I start by writing out, say, the first 1, 2, 3, 4 terms to kind of get an idea of what this is looking like, plug in 0, 1 over 2 to the 0 is 1, x minus 3 to the 0 is 1, so the first term would be a 1. And then n is 1, would be 1 over 2 to the first, x minus 3 to the first, so on and so forth. So I get these first 4 terms here, and of course, plus dot, dot, dot. But at least the first 4 terms kind of give us an idea of what the pattern looks like. Now, what I can do is, let's differentiate this expansion. Okay, all we need is the power rule. If I differentiate 1, of course I get 0. Differentiate this one right here, I'm going to get a half. Differentiate this next term, power rule 2 comes down, so it's 2 quarters. It does reduce to a half, but same thing with like this. This next one we would have 4 over 9. Well, I guess that one doesn't reduce, but eventually some of those fractions will reduce. What I want to do is I don't want to simplify, because simplifying actually is going to lose some information. At any rate, the next one, 3/8 x minus 3 squared plus dot, dot, dot. So I want to write out at least the first 3 to 4 terms, probably at least up to the third term, but probably the fourth term is helpful, to get a pattern of what the derivative looks like. Now, if I look at these terms here, let's look at what's happening. Each one of these has a fraction. So again, the 0 plus, we can actually just erase that. Series starts here. Well, it looks like we have a fraction, and then I'm going to have powers of x minus 3. Okay, well, let's see. The numerator of the fraction, 1, 2, 3. In other words, so I could just label that as n. And then let's compare the numerator with the exponent. So notice I've got 2 to the, and then to the first, 3 to the second. That means the exponent is 1 less. That means the exponent, I'll make that n minus 1. And then what about the denominator? Well, 2, 4, 8, those are all powers of 2, meaning I'll write this as 2 to the n. Notice if I have, say, n is 2, that'd be 2 over 2 squared, 3 over 2 to the third, so on and so forth. Now let's look at the initial index value. Where does this start? Well, the first term has a 1 on top, so that'd be n equal to 1. And then notice if I expand this out, this would match this exactly. If I plug in 2, I get 2 over 2 squared, which would be 2 over 4, x minus 3 to the 2 minus 1, which is 1. Okay, so this right here would be the summation notation for the derivative of this expansion. Okay. We'll summarize this here in a moment, but basically all I did is I took this infinite series, I expanded it out using the first 4 terms, differentiated the expansion, and then rewrote the expansion as an infinite series. Okay. And again, what we want to do is basically go from the original power series to the derivative without these intermediate steps. Let's look at one more example before we do that. Next example, let's take a look at 1 over n factorial, x to the 2n plus 1. If I write out the first 1, 2, 3, 4 terms again, n is 0, 1 over 0 factorial, x to the first, 1 over 1 factorial, x to the third, so on and so forth. As a quick reminder, 0 factorial is defined to be 1. So I'm not dividing by 0 here. Remember, 0 factorial is 1. Now if I differentiate this expansion, of course this fraction here, 1 over 0 factorial is 1, so that's 1 times x. The derivative of that would be 1. Continuing along the terms here, the derivative of this second term, 3 would come down, so it'd be 3 over 1 factorial, x to the second. 5 over 2 factorial, x to the fourth, so on and so forth. Now let's rewrite this as an infinite series. Well, again, what is the pattern? If I look at, say, these consecutive terms here, this one, of course, doesn't really give me any information, but we can see going along the sequence here, or these terms, I probably shouldn't use the word sequence there. If I go along the terms here, we see that each denominator has a factorial, so let's put a factorial there. And then I've got powers of x. And now let's kind of fill in what we see. Well, let's start with the denominator. It looks like we would have, say, we could pretend this is 0 factorial, 1 factorial, 2 factorial, 3 factorial, so it looks like it's, say, going to be n factorial. Now, how is the numerator and the exponent? Well, let's look at the exponent first. How is the exponent related to this? So notice I've got 1, 2, 2, 4, 3, 6. So that means that the exponent is actually double this one. So your exponent would be 2n. Now, how is the numerator related to the exponent? Well, 2, 3, 4, 5, 6, 7. That means that this numerator is 1 more, meaning I have 2n plus 1. And then what is the initial index value? Well, if I plug in, let's just try it. If I plug in 0, I'm going to get 1 over 0 factorial x to the 0, which is 1. If I plug in 1, I get 3 over 1 factorial x squared, which is this one. So therefore, it does start at 0. Okay. Now let's take a look at a summary of that. Before I write the summary, let's look at what we did with each of these two examples, looking at the original series going to the differentiation result. Well, going from here to here, if I just ignore this and just use the power rule, n is going to come down and then it's going to just reduce by 1. So I've got n over 2 to the n, x minus 3 to the n minus 1. This is what we would get if we just use the power rule on this term. Over here, one more comment on that, though, here in a second. Same thing up here. If I just differentiate, if I just ignored the summation and use the power rule, we would get 2n plus 1 over n factorial x to the 2n, which is exactly what we have here. One thing to notice is the initial index value. Here is a 1, here is a 0. Now, the difference is the reason this starts at 1 is because, remember, the first term was a constant, was 1. So that term actually disappears, meaning in my expansion, we don't start with the n equal to 0 term. With the derivative, we're actually going to start with the n equal to 1 term. And in fact, if I was to plug in n equal to 0, this would just all be 0 anyway. So we start with the n equal to 1 term. Now over here, the very first term was not a constant. So when I differentiate, I do start with 0. Now let's summarize. If I differentiate a power series, what I'm going to do is two things. I'm going to take the derivative of this term here, just like you did back in Calc 1, just using the power rule. That would give you n cn x minus a to the n minus 1. I just differentiate that term using the power rule. Now, what you have to check, though, is the initial index value. This could be 0 or 1, depending on if the first term is a constant. And you can quickly check that. If I plug in n equal to 0 here, just to check my first term, I'm going to have, well, really, this is always going to be a constant, but I'll just have to check this power term. If I plug in 0, I get x minus 3 to the 0, which is a 1. Over here, if I plug in 0, I get x to the first. Again, if the first term is a constant, then your derivative of the series is going to start with a 1. If the first term is not constant, the initial index value will stay the same. Okay, let's work through a couple examples. me dry that off a little bit better, because sometimes the marker doesn't write well if it's even slightly damp. So clean this up. Okay. Let's take a look at an example of differentiating a geometric series. So first and foremost, recall a geometric series has the following form. It's the sum from n equals 0 to infinity. A r to the n is a over 1 minus r, provided that the magnitude of r is less than 1. Okay, so let's take a look at differentiating a function defined as a geometric series. For example, let's take the simplest possible function. F of x is equal to the sum n equals 0 to infinity of x to the n. Now, of course, this is also equal to, well, in this case, a would be 1 and r would be x. So this would be the function 1 over 1 minus x, again, provided that the magnitude of x is less than 1. Well, let's differentiate this series. So differentiating the series. All right. So this means that the derivative of the function f prime would be, well, let's fill this in. First and foremost, if I plug in 0, I get x to the 0, which is 1. That's a constant. That means the derivative is going to start at 1. And then just use the power rule. So that would be nx to the n minus 1. Right? So this would be the derivative of this. All right? On the other hand, f of x, which is this infinite series, is also given by 1 over 1 minus x. Well, we can differentiate this as well. Again, we can either use the quotient rule or power rule with the chain rule. So let's think of this as 1 minus x to the minus 1. And then if I differentiate that, I'm going to get negative 1 minus x to the negative 2, and then chain rule negative 1 pops out, giving me, so negative is positive, I get 1 over 1 minus x squared. Well, if f prime is this and f prime is this, that means that this is equal to this. What that allowed me to do is I actually was able to generate a power series for this function. So summarizing, 1 over 1 minus x squared is equal to the sum 1 to infinity nx to the n minus 1. In other words, differentiating power series, if I have the original series, I can write it as a function. I can generate power series for other functions using that technique. Okay, but again, basically the idea is that I just differentiate this using a power rule, which is honestly probably the simplest differentiation technique that you learned in your Calc 1 class. And then all I have to check is the initial term is either going to be 0 or 1. Now, of course, I could have a power series that starts at, 2, 3, 4, 5, whatever the case may be. And so in that case, I would just generalize this by saying if this starts at 3 and the first term is 0 or is a constant, then this would just go up 1. So that'd start at 4. If this starts at 5 and the first term is not constant, then the initial index value would stay the same. Okay. So again, differentiating a power series is a pretty simple procedure. It just looks a little notationally heavy, but again, it's just the power rule at the end of the day. Thanks for watching, and please consider subscribing.